Right, so today we're going to have a look at one of the examples that we did in class. So the question asked us to solve x cubed plus 3x squared minus 3x minus 1 equals 0. And we were asked to use the substitution x equals tan of theta. So from that it would follow that tan cubed theta plus 3 tan squared theta minus 3 tan theta minus 1 equals 0. Now, if we have a look at what our result was in question B part 3, it looks very similar apart from a few things. We're going to try and manipulate this to get what we had in part 3. So if I do that, I plus 1 and minus 3 tan squared theta to the other side, we've got that. Now the left-hand side from this looks very much like the denominator in the previous question we did. So if I divide that to the other side, I've got tan cubed theta minus 3 tan theta over 1 minus 3 tan squared theta equals 1. Now we're really close because the denominator is the same as the previous question, but the numerator is not. It's almost the same, though if I flipped it and wrote it backwards, it would be the same. Now we can do that by multiplying both sides by minus 1. So I've got 3 tan theta minus 10 cubed theta over 1 minus 3 tan squared theta, and that's equal to a minus 1 now. Now that's exactly the property that we had in the previous question. So we can say that the left-hand side now is equal to tan of 3 theta, and that equals minus 1. That's because in the previous question we had proven that this was equal to tan of 3 theta. Now minus 1 implies that we're in the second and the fourth quadrant. Now hopefully by now we have memorized that tan of theta equaling 1 means theta is pi on 4. But since we're in the second and the fourth quadrant, we're going to say 3 theta is equal to 1 or pi minus pi on 4, which is 3 pi on 4, or 2 pi minus pi on 4, which is 7 pi on 4. Remember though, we're going to plus 2 pi to both of those answers, so 3 on 4 plus 2 pi, we get 11 pi on 4. 7 on 4 plus 2 is 15 pi on 4. And if we then plus 2 pi again to both of those solutions, 11 on 4 plus 2 pi, we get 19 pi on 4. And 15 on 4 plus 2 is 23 pi on 4. So those are our values of theta. If we divide by 3, we get theta is 3 pi on 12, 7 pi on 12, 11 pi on 12, 15 pi on 12, 19 pi on 12, and 23 pi on 12. So therefore our solutions, those are all of our solutions for theta. And now since we let x be tan theta, therefore x is tan of 3 pi on 12, 10 of 7 pi on 12, and so on. Now please in an exam write out all of those solutions, but it just follows that it's going to be tan of all of those angles. Now part D asks us to show that tan of pi on 12, tan of 5 pi on 12 is equal to 1. Now if we're solving polynomial equations and we get the product of two things that we kind of saw as the answer to those polynomial equations, we're going to think about the product of the roots. If we're asked to find the sum of these things, of course we're going to do the sum of the roots. Let's write out some of the solutions to that equation we got from above. We got x is tan of 3 pi on 12. Now 3 pi on 12 is 1/4, so x is tan of pi on 4. We also get tan of 7 pi on 12. And then the next solution was tan of 15 pi on 12. So we're going to have a look at some of our solutions here. So, I missed one actually, excuse me. We've got 10 of 11 pi on 12. All right, so those are our first three solutions there. Now, let's write out, we might write out the next one as well, 10 of 19 pi on 12. Now, all of these answers, there's an infinite number of solutions to this polynomial equation, and that's because trigonometric functions repeat. They have a period, and they repeat after that period, and they're exactly the same. So this is the same as this, which is the same as this, and this is the same as this, which is the same as this. So we're going to try and play around with some of these to see if I can get pi on 12 and 5 pi on 12. So if I have a go at drawing 7 pi on 12, it's going to look something like that. 7 pi on 12 is there. Now that would follow that this angle here is 12 minus 7, which is 5 pi on 12. So we're going really well at the moment. We've got x is 10 of pi on 4. Now 10 of pi on 4 is 1. So x is 1. Now we've got x is also 10. We figured out that 7 pi on 12 was also 5 pi on 12. But we're going to make that a minus, and that's because it's now in the second quadrant, and 10 is negative in that second quadrant. So we've got minus 10 of 5 pi on 12. And then what we've got after this is we're going to look at our 11 pi on 12. Now, 11 pi on 12, if I write this out again, start again. 11 pi on 12 is here. So that's 11 on 12, pi on 12, which would make this pi on 12. But pi on 12 is something else that we're looking for. So 11 pi on 12, we get that acute angle is pi on 12, and that's because pi minus 1 on 12 is pi on 12. Pi minus 11 pi on 12 is 1 on 12, or pi on 12. So we've got our second solution is 10 of pi on 12. But again, we're now in the second quadrant, so that makes 10 of minus pi on 12. Now we're basically there because we don't need to consider any more of our solutions, because we've figured out that two of my solutions are equivalent to what we were after in the question. So if we consider the product of the roots, the product is going to be 1 times minus 10 of 5 pi on 12 times by minus 10 of 5 pi on 12. Oh, I meant to say pi on 12. Now if we go back to our original polynomial equation, we had x cubed plus 3x squared minus 3x minus 1. You should know that's going to be minus plus minus. So the product of the roots is going to be minus 1 over 1. So minus 1 over 1 is 1. So the product of the roots is equal to 1. Those two minuses will cancel. And we've got 10 of 5 pi on 12 times 10 of pi on 12 is equal to 1. And we're done. QED. Right. Hope that makes sense. Thank you.